These are the notes on oxidation reduction reactions, part 1. So we are going to do a very short unit here, looking at chemical reactions in a somewhat different way. Some would say this is a deeper level of chemistry, or at least an alternative way of looking at reactions, looking at them as all about the possession of electrons. We call these reactions oxidation reduction reactions because if you have oxidation, well, you need to have reduction as well, so they go hand in hand. Sometimes we look at them in terms of half reactions, but the half reactions cannot happen without the other half. So oxidation reduction has to do with the possession of electrons. Somebody gains, somebody loses. If you lose completely or just in part one or more electrons, that is oxidation. So oxidation is losing electrons. Oxidation is a reaction that removes one or more electrons from a substance such that the substance's valence or oxidation state increases. Now that's the confusing part, because you are losing something and yet something is increasing. So oxidation states can be a little bit confusing. You often have to reverse yourself, and that's why some people have trouble with this topic. I will give you a number of ways that you can remember this as we go forward. On the flip side, the gain of electrons is described as reduction. Reduction is a chemical change in which electrons are gained, either by the removal of oxygen, the addition of hydrogen, or the addition of straight out electrons. One way or the other, electrons are gained. So it turns out, if somebody's gaining them, well, somebody else must have had to lose them. And so these two go hand in hand. An obvious example of this, although honestly not always the way that this compound forms, is a simple reaction between sodium and chloride. Sodium and chloride have vastly different electronegativities. Sodium, being a metal, an alkali metal, has extremely low electronegativity. Chlorine, being a halogen, has one of the highest electronegativities. In fact, it's the third highest of any element. So when they get together with each other, it's just not a fair battle. Chlorine is clearly going to be hogging those electrons. This forms what we call an ionic bond. So when an ionic bond forms, no matter what, there's definitely an imbalance in the pull on electrons. A huge difference of electronegativity, large enough for the electrons to be completely transferred. So going from the native element sodium and chlorine as we find it as chlorine gas into the compound sodium chloride is definitely an oxidation reduction reaction, because we have changed the possession of the electrons. Another way to say that is that we've changed their oxidation states of the sodium and the chloride. We've changed their oxidation states. So clearly this is not the balanced equation, the true equation for this reaction. A lot of times I will give you the skeletal form of the equation and you will have to balance it. But you can see what's happening here. We've got the native element sodium, very hazardous element to have around because of its extreme reactivity, and chlorine gas, another really hazardous chemical to have around because its reactivity is so extreme. Putting those together, you'd expect to get a super monster. Put together two monsters, you'd expect to get a super monster, but very much like we saw with acid-base neutralization, by forming an ionic compound made of ions, we wind up with a much, much let's say, safer, less reactive chemical in the compound sodium chloride. Okay, compared to the lion and the dragon sodium and chloride, sodium chloride, the compound, is like a little sheep. Very, 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 very tame in comparison. So when we balance this equation, well, then it becomes clear what is really going on. For every 2 atoms of sodium, you have 1 molecule of chlorine gas. They are reacting with each other, and they are forming 2, what's that word? Oh yeah, formula units of sodium chloride. Remember, that's the crappy term that we use to describe that little repeating unit that makes up a salt crystal. So you never actually find them on their own, by the way, not even 2 of them like that. They're just embedded in the crystal lattice, like the picture you see behind the equation. So this is what's really happening when sodium reacts with chlorine, forming sodium chloride. 2 monster chemicals making a comparatively tame chemical. However, forming ionic bonds, which is an obvious transfer of electrons, isn't the only way to transfer possession of electrons, at least partially, as we can see in this reaction, carbon plus oxygen. What kind of reaction is this, by the way? Which of the 5 types? Well, it's a reaction with oxygen, so it is combustion. So this is the combustion of carbon. But if you notice, it's a weird product there. That's not what you were expecting, is it? Carbon monoxide. Now, this will happen under situations when the supply of oxygen is very limited. And you will inevitably get a little bit of carbon monoxide under normal combustion situations, just because depending on where the carbon is located, it's not always going to have access to adequate oxygen. So the interesting thing about this reaction is that carbon is starting out on its own, oxygen is starting out on its own. Let's say they're in possession of their own electrons. But then after they combine into carbon monoxide, now we have a polar covalent bond. Why is it polar? Well, because oxygen, of course, is the silver medal winner for electronegativity, and carbon just can't keep up. So because carbon is significantly different from oxygen, it does generate a polar bond. Now in carbon dioxide, those polar bonds wind up canceling out, but in carbon monoxide, they do not. So carbon monoxide has a very, very different nature than carbon dioxide. It is a polar molecule. Here we can see the reaction, the skeletal reaction, carbon plus oxygen producing carbon monoxide. And again, you don't want to be around too much carbon monoxide because it can cause you to asphyxiate. It can cause you to basically suffocate. So you want to avoid it as much as possible. And we get a little bit exposed to a little bit when we're near a road, on a freeway. You're exposed to always little bits, but as long as it's not a huge amount, your body can usually handle it. Let's balance this. What do we need to balance this? Well, obviously we got 2 oxygen on the left. We need 2 carbon monoxide on the right, and that'll double the carbon, so then we have to double the carbon on the left. Like so. So again, it's interesting how so many chemical equations just balance with coefficients of 2, like maybe 1 or 2 of those. Really simple to balance, not the really hard ones that we used as practice when we were learning techniques for balancing. This is much, much easier. Okay, so 2 carbon atoms react with 1 oxygen molecule, producing 2, let's call them molecules of carbon monoxide, okay, or free radicals. And those carbon monoxide, lucky for us, they won't last too long in the atmosphere because they will react with the other oxygen around and eventually turn into, most likely, carbon dioxide. So now in the compound, you have changed the possession of the electrons, because now there is a fight between the carbon and the oxygen over those electrons. Clearly, oxygen is winning that fight. So has the oxygen really stripped electrons off the carbon? Well, sort of. Not completely, but partially. And in oxidation reduction, partially counts. So if oxygen has gained partial possession of electrons, that changes its oxidation state. So if you remember back when we were learning about the different kinds of bonds, there are some bonds that are just perfectly fair. Those are the nonpolar covalent bonds. In nonpolar covalent bonds, the electrons are shared evenly, and nobody has really gained any possession whatsoever of any electrons. However, in the other kinds of bonds, like polar covalent and ionic, that is not true. In a polar covalent bond, it is not quite fair because one side with the greater electronegativity is hogging the pair of electrons and gaining possession of that pair. So when you form a polar covalent bond out of pure atoms, okay, or molecules of pure elements, you will inevitably have some kind of oxidation reduction reaction. The same thing goes with ionic bonds. Talk about unfair. The electron is completely stolen in an ionic bond. So if you form an ionic bond out of the constituent elements, okay, or molecules of pure elements, it has got to be an oxidation reduction reaction. Also, if you break a polar covalent bond and decompose that molecule into its pure elements, that has also got to be an oxidation reduction reaction. And the same thing goes with an ionic compound. If an ionic compound is broken apart into its constituent elements, okay, back to their original elemental form, that has got to be an oxidation reduction reaction as well. So not every single reaction in chemistry is oxidation reduction, but quite a lot of them are. And if you remember those rules of thumb from electronegativity differences, a covalent bond is going to form between two nonmetals, because the difference of electronegativity between any two nonmetals is never great enough to make an ionic bond, unless, of course, as you learned later, they are found in polyatomic ions that collectively have a greater difference of electronegativity, like ammonium nitrate, which contains only nonmetals and yet has an ionic bond between them. Okay, so often when we're talking about oxidation reduction, we're talking about polar molecules or ionic compounds as the reactants or possibly the products. A good example of this is the decomposition of mercury oxide, HgO. When mercury oxide is heated, it will decompose into elemental mercury, which of course is a liquid metal, and oxygen, which is a molecular gas. So in order for this to happen, you're going from a compound where mercury and oxygen are combined to their individual constituent elements. And in the molecule, oxygen, of course, has a great advantage, has greater possession of the electrons. But that ceases to be the case when mercury is on its own. No one is really taking mercury's electrons anymore. So now mercury has a greater possession of electrons. So in this situation, going from HgO to Hg, mercury atoms are reduced. Also, oxygen atoms going out of HgO into O2 molecules, they are oxidized. Now I know it's funny to keep track of what that sounds like and what it means, but it has to do with the possession of electrons. If you are reduced, you have a greater possession of electrons. If you are oxidized, you have less possession of electrons. Okay, so I know it seems a little confusing here. So any single reaction like this one, in which an oxidation and a reduction happen, is called, of course, an oxidation-reduction reaction. But oxidation-reduction reaction takes so long to say, they had to come up with a shorter way to say it, and that is a redox reaction. So a redox reaction is the same thing as an oxidation-reduction reaction. It just saves you a lot of syllables, and they swap it around because it sounds better. They swap around the red from reduction and the ox from oxidation, redox, okay? Redox reactions. But clearly this reaction isn't balanced here. So let's see, well, there's 2 oxygen atoms on the right side. There's only 1 oxygen atom on the left. So that means we're going to have to double the mercury oxide. And then if we double that, that'll give us twice as much mercury. So we'll have to double the mercury. Oh, that's easy. Once again, just requires a few 2's to balance the chemical equation. And mercuric oxide is to differentiate it from mercurous oxide, which is Hg2O. Okay, but let's not worry about that right now. And so you can see that in the compound, mercury is losing out to oxygen in its possession of electrons, but in its pure form, it's not losing out to anybody. Oxygen has an advantage in the compound, but when it's fighting another oxygen, it has no advantage. So that's a good way to think about redox reactions. It has to do with, are they in possession of electrons as much as they were before, in the reactants as in the products? If that changes, then it is a redox reaction. So to keep track of redox reactions, we use something called oxidation numbers. Now, oxidation numbers are actually a little bit confusing when you talk about their strict definition. However, there's an easy way to figure them out. Very frequently, there's a very easy way to figure them out. Okay, so to identify whether atoms are oxidized or reduced, chemists use a model of oxidation numbers, which can help them identify differences in an atom of an element in different compounds. So the oxidation number is the number of electrons that must be added to or removed from an atom in a combined state to convert the atom into the elemental form. Now I know that is a little bit confusing, but you'll see that there's a much easier way to figure out the oxidation number. So by following the sets of rules, you can assign an oxidation number to each atom in a molecule or an ion using the ones that we know, and then you can figure out the remaining ones. So it's the number of electrons that must be added or removed to get it back to what it is on the periodic table. Let's just say that. But you'll see there's a much easier way to determine the oxidation numbers. So the thing about oxidation reduction, if you weren't clear like why it's even called that, well, the oxidation number of an atom, when it increases during a reaction, it is oxidized. If the oxidation number of an atom decreases, the atom is reduced. That is why it is called reduction, because a reduction is a drop, right? So it's a decrease in something. Oxidation number is what it's a decrease in. It is not a decrease in electrons. Okay? So how do we assign oxidation numbers? We're going to identify the chemical formula. Like basically you need the chemical equation. Assign the known oxidation numbers. Some elements always have the same oxidation numbers in compounds. And then you can calculate all the remaining ones using the known ones. I'll show you how to do that in the next notes. So remember, it's a little tricky, the terminology, but the reason it's called reduction is because it's a decrease in the oxidation number. And you will see shortly that there is a much easier way to determine the oxidation number than what I said on the previous slide. There's a much simpler way to figure it out. So that is the end of Notes on Oxidation Reduction, Part 1.